Hello, welcome to another module in this massive open online course on estimation for wireless communications. In the previous module, we looked at estimation of the channel coefficient for a wireless communication system, alright, and we have considered the maximum likelihood estimation of the channel coefficient in a wireless communication system, and we have been able to demonstrate that the estimate of the channel coefficient h hat, where h represents the channel coefficient is given as h hat. So, we are looking at wireless. So, we are looking at wireless channel estimation. In fact, we also said this is a key process or a key aspect in wireless communication. This is known as wireless channel estimation, that is estimation of the channel coefficient, and we have shown that the maximum likelihood estimate of the channel coefficient is given as h hat equals x bar transpose y bar divided by x bar transpose x bar, where the vectors y bar equals the vector, the observation vector, that is the vector of observations y1, y2, so on up to yn. So, this is your observation vector, and x bar equals x1, x2 up to xn, and this is your vector of pilot symbols. Vector of pilot symbols. Remember, we said x1, x2, xn are the pilot symbols that are transmitted for channel estimation. So, x bar is the vector of pilot symbols. Also, we can call this as the pilot vector. So, we are saying that the channel estimate h hat is given as x bar transpose y bar divided by x bar transpose x bar, where x bar is the pilot vector and y bar is the corresponding observation vector, that is the output symbols corresponding to the transmitted pilot symbols x1, x2 up to xn. And you can see that this can also be written as now you can see, I think we have already seen this before, that is, if I look at x bar transpose x bar, that is nothing but basically your row vector x1, x2 up to xn times the column vector x1, x2 up to xn, which is x bar transpose x bar. This you can see is nothing, is basically summation. This you can see is basically x square 1 plus x square 2 plus so on up to x square of n, and this quantity you can see is basically nothing but the norm of the vector, norm x bar square, where x bar is your pilot vector. This is also basically your summation k equal to 1 to n x square of k, and this is basically your norm of x bar square. So, x bar transpose x bar, of course, this is a standard result, and we have also seen this before, that is, if x bar is a vector, that is a real vector, remember that is what we are considering to begin with, x bar transpose x bar, which is summation k equals 1 to n x square k, which is nothing but the norm square of the vector x bar. Therefore, I can also write it, the estimate, the maximum likelihood estimate, in a compact fashion as x bar transpose y bar divided by x bar transpose x bar, which is also basically your x bar transpose y bar divided by norm of x bar square. Okay. Now, also let us go back to our model, let us go back to our pilot observation, that is the pilot input output model, that is the input output model. Our input output model, remember, recall, is yk equals h times xk plus vk, where yk is the observation, h is the channel coefficient, xk is the transmitted pilot symbol, and vk is the corresponding Gaussian noise sample. Therefore, now I can write y1 equals h times v1, h times x1 plus v1, y2 equals h times x2 plus v2, so on, yn equals h times xn plus vn. So, we have y bar, which is basically now vectorizing this to write it in a compact fashion. We have y bar equals h times x bar plus v bar. We have seen y bar is the observation vector, x bar is the pilot vector. Now, we have v bar, and this is the noise vector. So, we can write this in a vector fashion, that is y bar equals x bar times h plus v bar, where of course, to repeat once again, y bar is the observation vector, x bar is the pilot vector, h is the channel coefficient, and v bar is the So, I have succinctly represented this as in a compact vector. Using vector notation, I have represented this in a compact fashion as y bar equals x bar times h plus v bar, where y bar is the observation vector, x bar is the pilot vector, h is the unknown channel coefficient, and v bar is the noise vector. Now, let us look at the properties of this noise vector v bar. So, we already said that each noise Vk is Gaussian. Further, we are going to assume that each Vk is IID Gaussian, then this also we have seen before, that is basically independent identical Gaussian. That is independent identically distributed as Gaussian, with each with mean 0 and variance sigma square, which implies again, to just summarize, the expected value of each Vk equals 0, expected value of V square k equals sigma square. Further, since they are independent, since the different noise samples are independent, expected value of Vk times Vk tilde, since they are independent, equals expected value of Vk times your expected value of Vk tilde if k not equals k tilde, and each of these expected values, is 0. Therefore, as a result, the net product is 0 if k not equal to k tilde. That is a correlation between two different noise samples Vk and Vk tilde is equal to 0 if k not equal to k tilde, since these different noise samples are assumed to be independent. Okay. Naturally, now let us characterize the statistical properties of the noise vector. The first property is simple, that is, if we look at the mean of the noise vector, that is, if I look at the mean of the noise vector, that is the mean of V1, V2 up to Vn. Now, naturally, each component is 0 mean, therefore, the mean of the vector is 0, that is expected value of V1, expected value of V2, so on, expected value of Vn. Now, each of these is basically equal to, the noise is 0 mean, so basically expected, this is the 0, this is simply the 0 vector. So, we can summarize this as basically the expected value of V bar is simply the, since each noise component is 0 mean, naturally the expected value of the noise vector is the 0 vector, that is simply said as 0. Yeah, it is understood that it is a vector, since we are talking about a vector. So, expected value of the noise vector is 0. Now, let us look at the variance. Of course, since V bar is a vector, we cannot look at the variance of a vector, we have to talk about the covariance of the noise vector, and that is defined for a 0 mean vector as follows. The covariance for our 0 mean noise vector is defined as Rv, that is the covariance is expected V bar transpose. For a scalar, we look at the square of the random variable. Now, since it is a vector, we are looking at expected value of V bar transpose, which if I simplify this is expected value of V1, V2, so on Vn, V1, V2, Vn times the row matrix V1, V2, Vn, the column matrix times the row matrix. This is sometimes also known as the outer product of the vector V bar transpose, which now if you can look at the entries of V bar transpose, if you look on the diagonal you have the squares of the various element V1 square, V2 square, so on V square n. The off diagonal entries are the cross products V2 V1, V1 V2. So, this is for instance V2, V1, V1, V2, so on up to V1, Vn. This product here will be Vn, V1 and so on. And now, if you take the expected value inside, you can see that the expected value of each of these diagonal elements, expected value of V square 1, V square 2, V square n, so on is sigma square, while the expected value of the off diagonal elements, since the different noise elements are independent, the expected values of the off diagonal elements, the expected, let me draw them with a different color, the expected value of the off diagonal elements, this you can see is clearly 0 because the different noise samples. So, these are independent. So, the only terms that are the only expectations that are going to survive are basically the expected values of the diagonal terms, which are basically the squares of the different noise samples. Therefore, the covariance matrix is basically the matrix n cross n matrix with sigma square on the diagonal, each diagonal element equal to sigma square, the rest of the entries 0. So, this is equal to basically your sigma square I. So, your covariance matrix Rv is equal to expected V bar transpose which is equal to sigma square times identity. Okay. So, we have the noise vector V bar which we have defined. The noise vector V bar is 0 mean, alright. So, expected V bar equal to 0, the 0 vector, and the covariance matrix expected V bar transpose is equal to sigma square times the identity, the n cross n dimensional identity matrix. So, sigma square times the n cross n dimensional identity matrix, and that is also clear because the noise variance is of size n, but we can also write this explicitly. So, this is identity matrix of size n cross n. Now, let us explore the properties of the channel estimate. So, let us explore the properties of the maximum likelihood channel estimate. So, we will start exploring properties of your ML, properties of the maximum likelihood channel estimate, and we know that y bar equals x bar h plus v bar, and we know that h hat equals x bar transpose y bar divided by norm x bar square, that is the expression that we have seen for the maximum likelihood estimate. Now, I am going to substitute the expression for y bar over here. So, I will have x bar transpose divided by norm x bar square times x bar h plus v bar, which is equal to, again now simplifying this, x bar transpose x bar divided by norm x bar square h plus x bar transpose v bar divided by norm x bar square. Now, if you look at this term, this is x bar transpose x bar, which is norm x square divided by norm x bar square. So, this is 1. So, therefore, net I have h hat equals h plus x bar transpose v bar divided by norm x bar square. Okay. So, what we have demonstrated that simplifying this expression for the maximum likelihood channel estimate, we have shown that h hat, the channel coefficient, estimate of the channel coefficient h hat equals h plus x bar transpose v bar divided by norm x bar square, where x bar is the pilot vector and v bar is the noise vector. Now, it is easy to see that if I look at the mean of the noise, mean of the estimate, that is expected value of h hat, that is nothing but your expected value of h hat plus x bar transpose v bar divided by norm x bar square. I am sorry, this is h, not h hat, h. Now, h is a constant, therefore, this is h plus expected value of course, x bar transpose v bar divided by norm x bar square, which is equal to now h plus x bar transpose expected value of v bar divided by norm x bar square. But now, we have already said that the noise vector is 0 mean. So, this quantity is the 0 vector. So, x bar transpose 0 bar is nothing but 0. So, I have net a very interesting property, that is h hat, expected value of h hat equals h plus 0, which is equal to h. So, summarizing, what we have is something that we have seen already in the context of your sensor network, where expected value of the estimate of the parameter is the parameter itself, that is expected value of h hat is equal to h, and therefore, such an estimate is known as an unbiased estimate, that is expected value of h hat is equal to h, therefore, such an estimator is known as the unbiased estimate. So, this is basically an unbiased estimator. This is basically an unbiased estimate, or this maximum likelihood estimate of the channel coefficient is an unbiased estimator. Now, let us look at the variance. Now, let us look at the variance of the channel estimate. Right? So, let us now look at the variance of the channel estimate. Now, we know that H hat equals H plus x bar transpose V bar divided by norm x bar square, which means H hat minus H, or H minus, or let us look at H hat minus H. If we look at H hat minus H minus H, that is equal to x bar transpose V bar divided by norm x bar square. Now, the variance is basically the expected value of the estimate is expected value of H hat minus H whole square, which is basically, I can write this. Now, this is a scalar quantity H hat minus H. So, this is equal to its transpose. So, H hat minus H square, I can write it as H hat minus H times its transpose. So, H hat minus H. So, what we are saying is this quantity, the channel coefficient, is basically a scalar quantity. Scalar quantity means it is basically a number. Therefore, expected value of H hat minus H whole square is basically expected value of H hat minus H times itself, which is expected value of H hat minus H times H hat minus H transpose, because the transpose of a scalar quantity or the transpose of a number is basically the number itself. But this will help us, this trick will help us greatly simplify the variance of the estimate as follows. And now, therefore, we can write this as substituting for H hat minus H from above. You can see H hat minus expected value H hat minus H is x bar transpose V bar divided by norm x bar square times x bar transpose V bar transpose divided by norm x bar square, which is equal to, now bringing this norm x bar squares outside, I have norm x bar 4, expected value of x bar transpose V bar times x bar transpose V bar transpose is V bar transpose x bar, which is now equal to, if I move the expected operation, the expectation operation inside, that is 1 over norm x bar to the power of 4 times x bar transpose expected value of V bar transpose x bar. And now, this is interesting because this is your sigma square I, which we already shown is the noise covariance. Therefore, this is 1 over norm x bar power 4 x bar transpose sigma square times identity, the sigma square will come out. So, I can write sigma square over here. X bar transpose identity x bar is simply x bar transpose x bar, which is sigma square norm x bar square divided by norm x bar power 4. This is basically your sigma square divided by norm x bar square, and therefore, we have an interesting expression for the variance, that is variance expected value of H hat minus H whole square is basically your sigma square divided by norm x bar square, sigma square divided by norm x bar square. So, we have derived the expression for the variance of the estimate. We have shown that the variance of the maximum likelihood estimate of the channel coefficient is sigma square divided by norm x bar square, where x bar is the pilot vector. Alright. So, this is the expression for the variance of the channel estimate, and further now we can characterize the distribution of the channel coefficient of the channel estimate H hat. Now, if you go back and look at H hat, for instance, you can see H hat is basically your H plus x bar transpose x bar V bar, which is a linear combination of Gaussian. So, this is a linear combination of and therefore, it follows that H hat in turn is Gaussian. That is, what is H hat? You can see H hat is basically this Gaussian x bar transpose V bar shifted by the mean, which is H. So, this is the mean of H hat, therefore, it follows that H hat is in fact Gaussian. We have shown that the mean of H hat is H. So, therefore, it follows that H hat is indeed Gaussian with mean H and variance sigma square divided by norm x bar square. So, it follows that H hat is, this is a Gaussian random variable with this mean and this, with this mean and this. So, it follows that H hat is a Gaussian random variable with this mean and variance. H hat is has a mean of H, which is the true unknown channel coefficient, and the variance is sigma square divided by norm x bar square. And this is also intuitive. This shows as the energy, this is inversely proportional to the pilot energy and directly proportional to the noise power. The noise power part is obvious. As the noise power sigma square increases, obviously the estimation error increases, and also it shows that as the energy in the pilot increases, that is norm x bar square increases, the variance of the estimate decreases, which is also very intuitive. That is, if you transmit more and more pilot power, naturally your estimate will be better and better. So, let us note that also this is inversely proportional, that is variance is inversely proportional variance is inversely proportional to the pilot power. Now, we have also seen that for a complex, how to extend this to a complex parameter, just again because we have said that frequently the channel coefficient is complex in nature. We have said the estimate of the complex parameter is simply replace the transpose by Hermitian, that is x bar Hermitian y bar divided by x bar Hermitian x bar, which is basically nothing but again x bar Hermitian y bar divided by x bar Hermitian x bar is once again norm x bar square, and this we had said is estimate for complex baseband channel coefficient, that is estimate for a complex parameter, estimator of your complex baseband this is the estimate of your complex baseband channel coefficient, that is when the parameter channel coefficient H is basically complex in nature. That is, you have to replace the transpose by the Hermitian, this is x Hermitian y bar divided by norm x bar square. Okay. And now, what is the variance? So, again you can derive the variance. We said variance will remain the variance of the complex parameter, that is variance is basically expected value of, now you cannot simply use the square, I have to use magnitude of H hat minus H whole square, the magnitude of H hat minus H whole square divided equals sigma square divided by norm x bar square, yeah, where we are assuming that each Vk, that this is important, each Vk noise Vk is complex zero mean symmetric. Remember, this is an important point, symmetric, which we talked about, symmetric Gaussian noise of variance sigma is complex zero mean symmetric Gaussian noise. Each Vk is IID. In fact, let us also emphasize that the various Vks are IID, independent IID complex zero mean symmetric Gaussian noise of variance. So, when the noise vector V bar is a complex symmetric Gaussian, so complex circular symmetric Gaussian noise vector, which means each Vk is basically IID complex Gaussian symmetric zero mean random variable of variance sigma square, which means the real and imaginary parts are zero mean independent and of variance sigma square by 2 each. Then we can also show that expected, that is basically the variance of the real and imaginary part, then it follows that variance of real part of estimate is equal to the variance of imaginary part of the estimate, which is equal to half sigma square divided by norm x bar square. So, what we are saying is basically it can be extended to a complex parameter h, that is complex baseband channel coefficient h, in a straightforward manner. First, the channel estimate h hat is x bar Hermitian y bar divided by norm x bar square, and further the variance of estimation of the complex parameter h hat is basically sigma square divided by norm x bar square, that remains unchanged, and the real and imaginary parts, that is the real part and imaginary part, have an estimation error of half of the net estimation error, that is half sigma square divided by norm x bar square. And also one can note that the estimation errors of the real and imaginary part are uncorrelated, and that is the last point, that is estimation errors of real and imaginary part. Further, of real comma imaginary parts are uncorrelated. Okay, that is a brief note for the estimation of the complex baseband channel coefficient h. So, in this basically module, what we have seen is basically we had started with the maximum likelihood estimate of the channel coefficient we have developed in the previous module and explored its various properties. We have shown that basically we derived the covariance of the noise vector V bar, and based on that we had shown basically that the noise estimate is basically, that the estimate of the channel coefficient is again basically it is an unbiased estimator, which means the expected value of h hat, the estimate, is equal to h, which is the true unknown underlying channel coefficient. Further, the variance in the estimate of the channel coefficient h is given as sigma square divided by norm x bar square, where norm x bar square denotes the total energy of the pilot signal, and therefore the variance is decreasing with increasing energy of the pilot signal or the pilot vector. So, we will stop here and continue with other aspects in the subsequent modules. Thank you very much.